All right, so let's get started. So we'll welcome back to everybody in Marcus and everybody live streaming in. I hope you guys had a nice spring break. We are moving along and we are finishing up some of our derivative techniques. So we have now finished the chain rule, which is what we get when we take the derivative of a composite function. And today we're going to tackle how we deal with functions that are multiplied or in a quotient. And so we haven't talked about those yet, but we did refer to them back when we started doing the derivatives. We said if things are separated by addition and subtraction, we can go ahead and do the derivatives term by term, but we have special rules for multiplication and division. So that's what we're going to be working on today. I do just want to give you a quick reminder that the Chapter 3 quiz is on Monday, so you will need to find a 1-hour period to complete that. There's a review tonight from 5 to 6 on all the techniques, and again on Monday from 4 to 5. Thanks for Moodle. So we are going to be covering, like I said, the last two rules today. I do want to give you a heads up. So we usually start the product rule at the end of the chain rule. And so I want to make sure we get the product rule and the quotient rule. So what we're going to be doing today is we'll do the first 4 examples of the product rule, and then we'll do the first 3 examples of the quotient rule. And then if we have time, we'll go back and do the other examples. But if we don't have time, those are posted on Moodle. You can watch the videos if you want to see them done out, or you can try them at home yourself or do them at Drop in Help if we don't get to them all. Okay, so I'm going to go ahead and switch over to the dot cam. Okay. And so we're going to start by talking about the product rule. So when we talk about a product in math, that means we have 2 things that are multiplied together. And in this case, we're talking about 2 functions being multiplied together. So you might have something like x squared times the natural log of x, or something of that sort. So one of the first things that we're going to be doing is we're going to be looking at our functions to see, do we have 2 things multiplied together, right? Identifying that we have 2 functions multiplied together. We could use limits, right, the definition of derivative, and apply it to f of x times g of x. And as we said before, mathematicians look for patterns in how these things work out algebraically. And from those patterns, we're able to give us a formula for what we're going to be doing with the product rule. So we're not going to go through the steps to get the formula today, but you can look it up if you're interested in sort of the background math. But what does the product rule formula look like here? So what this says is if you have f of x times g of x, so you have 2 distinct functions and they're multiplied together, and you want to take the derivative of that product. Well, this rule says it's the derivative of f times g, so the derivative of the first term times the second, plus f of x times g prime of x. So this has the derivative of the second term times the original of the first. Okay, so again, one of the key things we're going to be starting with is identifying that we have 2 things multiplied together. So what we're going to do is we're going to go very, very thoroughly and carefully through example 1 together, because I want to set up a good process and set of habits for you and how you may want to structure this. Okay, so I'm going to raise this up a little bit. I think it'll be a little bit easier to see. Okay, so we can see how we're going to apply this formula. And so we're going to start with this example, x squared times e to the x. Okay, so the very, very first thing that we need to do is we need to determine that we have 2 functions multiplied together, right? So the other option is that maybe we have a chain rule, right, which comes from a composite function. One of the easier ways to determine if you have 2 things multiplied together is you can literally separate them with a line, right? You have something on the left, something on the right. So here, my 2 functions are x squared and e to the x. I can draw a line down the middle, and that completely separates the 2 functions that I'm multiplying together. Okay, so once I've determined that I have 2 functions multiplied together, one of them I'm going to call f of x, and one of them I'm going to call g of x. The product rule is not so picky, because when we use the product rule, we're using addition and multiplication. So it doesn't actually matter which one is your f of x and which one is your g of x. You will get the same answer. but the convention is typically that the first function you see is your f of x, and the second function you see is your g of x. So over on the side, I'm going to write f of x equals x squared, and g of x equals e to the x, okay? And now I usually put these side by side. And what I'm going to do is I'm going to take the derivative of each piece, because when I use my formula, notice that I have the derivative of different terms. So when I do the derivative in a product rule, in a quotient rule, I always write it underneath the function. And the reason I do that is because later on, if you go to take Math 128, you're going to be undoing derivatives. And sometimes having this idea of above and below to help you indicate direction can be helpful. Do you have to do it this way? No, but I find it helpful. So I'm going to do the derivative of each term underneath the function that I've written down. Okay, and so the idea with the product rule is that when we separate them into f and g, is that it's easier because now these are basic functions, which we know how to take the derivative of. And again, basic does not mean easy, basic means foundational. So the derivative of x squared, we're using a power rule here. So that's going to give me 2x. Over here, I have e to the x. That's from our exponential derivative rules. The derivative of e to the x, we know, is e to the x. Okay, so now I have all 4 pieces that I need for my formula. So here, I was doing the derivative of y equals, so I'm looking for y prime. And so my rule says f prime times g. So I have f prime times g. So that's going to be 2x times e to the x. That's that first part of the formula here. And then plus, now I'm going to do f times g prime. So f is here, g prime is here. So f, which is x squared, times g prime, which is e to the x. So my derivative of this function looks like this: 2x times e to the x plus x squared times e to the x. If I'm just taking the derivative, it looks like this. Sometimes we do factor this. We will do a lot of factoring of derivatives in chapter 4. So while you may not have to do a lot of it now, it's good to sort of have an idea of what that may look like. So I'm going to go ahead and show you what a factored answer might look like. But just, if you're doing this on Wiley or something like that, this is totally fine, okay? If I wanted to factor this, I'm looking for what's common in both my terms. So notice that both the terms have an e to the x, so that's something in common. And then both of my terms have an algebra term. The first one has an x and the second one has an x squared. So I can pull out an e to the x and an x term here. Okay, so I'm going to pull out an x, not an x squared, because you pull out the lowest power when you have things that are the same base. And I'm going to pull out an e to the x. So once I've pulled those out, I go to the first term and I say, what's left? Well, if I take out the x and the e to the x, the only thing left is 2. And then I go to the second term. If I pull out an x and an e to the x, the only thing left is one single x. So I can write it like this. These two mean the same exact thing, okay? They are mathematically equivalent. One is not more correct than the other. The reason we factor things is that we may be using it to solve for something further in a process, okay? So that's what the product rule looks like. We're identifying the 2 functions being multiplied together. We call the first one f, the second one g. We take each of their respective derivatives, and then we're going to put it back together in the formula. Okay, so I'm going to have you try one now. Okay, so here we're looking at the function ln x times e to the 6x. So there's 2 things I want to remind you of. First, we want to make sure it's a product rule, right? So we can draw the line down the middle so we know it's a product rule. You don't have to draw a physical line. It's just a reminder if you're not sure. And so the second piece I want to remind you of is e to the 6x. If you have a constant up in the power, I just want to remind you that that kicks in something special when you do the derivative, that 6 will come out and multiply in front. Okay, so I'm going to give you 2 minutes. I'd like you to try to set this up just like we did the last one and see if you can put it all together to get the derivative using the product rule. So try that out, take about 2 minutes, and then we'll go through it together. Okay, take about 30 more seconds. All right. So again, the first step was just identifying that we needed to use the product rule. So we have 2 things multiplied together. We're going to call the first term f of x. So that's going to be the natural log of x. The second term is going to be g of x. So that's e to the 6x. Now we need to take each of their respective derivatives. So remember the derivative of ln x, that's from our chart. So the derivative of ln x is 1 over x. And the derivative of e to the 6x is e to the 6x, but then a 6 comes out from that constant up in the power. So I'm going to put it in the front. You might have put it on the other side. That doesn't matter which side it's on, but it does have to multiply the function. Okay, so now we need to put all of these things back together to find our derivative. So again, we're going to do f prime times g. So here we have 1 over x times e to the 6x plus f of x times g prime of x. So we're going to multiply this way. So natural log of x times 6e to the 6x. So again, this is totally fine. This is your derivative. This is mathematically correct. We could factor this. The only factor that is in both terms is the e term. So if we were going to factor this, we would pull out e to the 6x, and we'd be left with 1 over x plus, now here we have a 6 and an ln x. Typically we write constants first, so we'd probably write this as 6 ln x. Okay, so that's just one way that you could factor it. Again, We're not going to be doing a ton of factoring in this particular section, but we will start doing quite a bit in chapter 4, which is why I'm sort of doing a little bit of it now. Okay, so again, that's an example of the product rule. So once we are comfortable with just sort of the general idea of the product rule, right, this formula here, we can use it to do all of the things we've been sort of typically doing with derivatives. So our next example here, right, find the equation of the tangent line. So we've done the tangent line problem a few times in a few different contexts. So we can do it again here, only now our function is going to be a product rule. So cosine x times e to the x at x equals 0. So as a reminder, we're looking for something in the form y equals mx plus b. We need a point and a slope. In order to get our point, we need to plug in our value into the original function. In order to get the slope, we need to plug our x value into the derivative. Then we can put it all together with y equals mx plus b. So I want you to try this out. Hopefully you remember this particular application in general, the process. And now we're just trying to apply the product rule within that. So I'm going to give you about 3 minutes to try this out. Again, feel free to look back in your notes to another tangent line problem if it will help. But go ahead and try that out, and then we will go through it together in about 3 minutes. Okay, take about 30 more seconds. Okay. So again, we're looking for a final answer in the form y equals mx plus b. And so we need a point and we need a slope. So the first thing I'm going to do is I'm going to plug my x value into the original function to get the corresponding y value. So I have cosine of 0, which is 1, times e to the 0, which is also 1. So that's going to give me 1, okay? Which means that my point is 0, comma 1, right? When x equals 0, y equals 1. Now, I also need the derivative in order to get the slope of my tangent line. So this is where my product rule comes in. So again, I could draw a line right down the middle here. I see I'm using the product rule. So I'm going to go ahead and set up a product rule to help me get ready for finding my derivative here. So my f of x is going to be cosine x. My g of x is e to the x. And now I need to find each of their respective derivatives. So we know from our derivatives list, the derivative of cosine is negative sine. And the derivative of e to the x is just e to the x again, okay? So when I put these together to get the derivative of the whole function, which I'm calling f, so don't be confused, this f and f prime are part of the formula, and now I'm putting it together to get the derivative of the full thing. So here, again, I'm going to do f prime of x times g of x. So negative sine x times e to the x plus f of x times g prime of x. So cosine x times e to the x. Okay, so I have all my terms, and now I need to plug in 0 because that's what I'm interested in, is what's going on at 0, right? So I'm going to carefully go ahead and plug in 0. Everywhere I see an x. Okay, so when I go through this and I look term by term, I want you to remember, so sine of 0 is 0. So this first term, the whole thing goes to 0. And then over here, cosine of 0 is 1, and e to the 0 is also 1. So I get 0 plus 1, which means that that all equals 1. So the slope of my line equals 1. Okay, so now I start putting it together. So y equals 1x plus b. So that's my slope. You don't have to write the 1. You can. It's up to you. Now I'm going to plug in my point. X is 0. Y is 1. So I have 1 equals 1 times 0 plus b. 1 times 0 is 0. So that tells me that b equals 1. So now I have my slope, I have my point, I have my b. I can put it all together to get the final equation of my life, which is y equals 1x plus 1. Okay, so again, whenever you do this type of problem, your solution should be in the form y equals mx plus b. We shouldn't have x squared or anything like that, because we're getting the equation of a tangent line. And so again, we find a point, we find a slope. When we find that slope, that's where we're trying out our new derivative, and we put it all together to get the equation of our line. Okay, so again, we've been doing this with all of our examples, and we will continue to use it. So just keep that in mind. The process is always the same. It's the derivative that is changing. So the next thing we want to be able to do is do second derivatives, right? And just like other derivatives we've done before, the way that we get to a second derivative is by finding the first derivative and then taking the derivative of that. So if we start with a product rule, we have the natural log of x times x to the fifth. We would need to use a product rule to find the first derivative. And then we would need to look through the first derivative to figure out what techniques we would need to use to find the second derivative. So what I would like you to do here is I'd like you to find the first and second derivative. And I will give you a little bit of a heads up. When you find the first derivative, you want to simplify anything you can before finding the second derivative. That's going to help you out if there's something you can simplify. Okay, so I'm going to give you about 30 minutes I want you to try this out, see what you can do. Even if you can only find the first derivative, that's a great first step, but try it out, see what you can figure it out, and then in about 3 minutes, we'll go through it together. Okay, take about 30 more seconds. Okay, so again, we notice that we're doing a product rule because we have two things multiplied together. And so we're going to go ahead and call the first one F and the second one G. And the hope is that when we separate them, they become derivatives we know how to take, which here we do. The derivative of ln x is 1 over x. The derivative of x to the fifth is 5x to the fourth with the power rule. Okay, so now we're going to put that together using the product rule. So our first derivative here, f prime of x, we're going to do f prime of x times g of x. So we have 1 over x times x to the fifth. Oops. Let me write that a little neater. X to the fifth, that's just a very large multiplication sign. Plus, then we're going to do f of x times g prime of x. So ln x times 5x to the fourth. And we get these two terms. And as I mentioned, if you can simplify the first derivative, it's a good idea to do that. And it turns out that we can. The first term, if you have 1 over x times x to the fifth, the x that's on the bottom here, one of the x's from x to the fifth, you get x to the fourth plus the natural log of x times 5x to the fourth. And the reason that I said that is because that's going to make the second derivative of this term a little bit easier to calculate, right? By simplifying. Now we just have to do a power rule on that term. So now in order to find the second derivative, this is where we have to be really careful and where things get a little more complicated. Okay, so we're looking for the second derivative. So we go to the first derivative and we're going to go term by term and try to figure out if we can find the derivative or if we have to use a special rule. So the first term is x to the fourth. X to the fourth is a derivative that we can take without any special rules, right? We can just use the power rule here. We don't have to use a chain rule or a product rule or anything like that. So the derivative of x to the fourth is 4x cubed. Okay. Now, when we go to the second term, we have ln x times 5x to the fourth. So we have two things multiplied together. Okay. So when we have two things multiplied together, we have to do a product rule. So we have to do the product rule on the second term here. So again, we just kind of go off to the side. The first function is ln x. The second function is 5x to the fourth. We find each of their respective derivatives. The derivative of ln x is 1 over x. Derivative of 5x to the fourth is going to be 20x cubed, because when the 4 comes down, it multiplies the 5 to give you 20, and then we subtract 1 power. So how do we put this all back in? So this plus is this plus, and when I do this, I usually write my solution to the product rule in parentheses, and that may seem like overkill, but it's particularly helpful if you end up with something with like a negative term or something like that, which we don't have here, but I find it good practice to make sure I can line up where my derivatives came from, and the parentheses help me. So you don't need them, but I find it helpful that when I'm doing a product rule, I put the full solution into parentheses so I can make sure that I've lined everything up right. Okay, so here, again, I'm going to go over here and I'm going to do f of x times g prime of x. So I have ln x times 20x cubed plus f prime of x times g of x. So 1 over x times 5x to the fourth. Okay, now can I simplify this? I could simplify this last term, right? This is similar to how I did it over here. This x can cancel out an x here. So it depends on what I'm trying to do, but I could simplify this term into 5x cubed. Okay, so this x will cancel one of these x's. I could factor this. I could factor out an x cubed term from the whole thing if I wanted to. I'm not going to. We don't do as much factoring in the second derivative. We do a little bit, but I'm going to wait till we actually need to use that to actually factor. So the only thing that might happen is just multiplication. Okay, so that's what the second derivative is going to look like. It takes a little bit longer. We need to be a little bit careful, but we can definitely do that. Okay. Okay, so now we're going to switch gears and we are going to jump over to the quotient rule. Depending on time, we may come back to the product rule. But we want to make sure that we know also how to do the quotient rule. So what is a quotient rule, right? Like what is a quotient? So let's start with that. So remember, the product is when we multiply two things together. A quotient is when you have one function over another function. So if you have something like, you know, some function over another function, that's called a quotient. We use it for division, right? So the question is, what if we want to take the derivative of a quotient? We want to take the derivative of one function divided by another function. Okay. Now this particular formula, again, derived by math by looking at lots of limits and things like that is a little more picky. And so first I'm just going to give you the formula, and then I'm going to talk about sort of what's picky about it so that we don't mess anything up. So the formula here is going to be f prime times g of x minus g prime times f of x divided by g of x squared. Okay, so this formula is using subtraction and division. And with subtraction and division, we can't swap out what term comes first, right? So 4 minus 3 is not the same as 3 minus 4. So that tells me that order is really important. So how does that get impacted here? So when we look at a function that is a quotient, we are always going to pick the top function to be our f and the bottom function to be our g for my formula to work out. And I have to be really careful about making sure I'm plugging in exactly like this. And so if this is not a formula that you will remember, you'll want to put like a box around it and a star so that you can quickly reference it whenever you're doing the quotient rule. Okay, so again, we're going to walk through an example together and do all the steps out really carefully, learning how to apply this formula. And then once you do it with one example, we can then apply it and use it for lots of other examples. So the example we're going to do together, we have e to the x over x to the fifth. I'm going to write this a little bit bigger. E to the x over x to the fifth. Okay, so again, the first thing I recognize is that it is a quotient, right? So I have one function divided by another function, right? So the first thing I see is that I'm having a quotient that I'm working with, and that's what tells me to use the quotient rule. Now I'm going to set up my work very similar to the product rule. So I'm going to pick my top function is always my f. So here that's e to the x. My bottom function is always the g. So that's the x to the fifth. Okay, so again, I'm picking one function to be f, one to be g based on where they're located. And then hopefully these functions are basic functions that I can take the derivative of. So here, the derivative of e to the x is e to the x. The derivative of x to the fifth is 5x to the fourth. Okay, so once I have all my pieces, now I'm going to go ahead and try to plug them into this rule. Okay, so let's see if we can carefully do that. So I have f prime times g. So f prime times g is e to the x times x to the fifth minus now g prime times f. So g prime 5x to the fourth times f of x, which is e to the x. So that's my numerator. And I have to divide that by g squared. So my g here is x to the fifth, and that term needs to be squared. Okay. Now, typically, we don't square this out. Right? In general, when we do the quotient rule, we leave this as whatever the term is squared. And when we look at the numerator, we only simplify sort of really obvious things. So like if you have like a 5 times 2, you would make it a 10. But otherwise, we don't futz a lot with it because the quotient rule already has a lot of places where we could mess things up because of the subtraction division. So we don't spend as much time simplifying it. We will, on occasion, factor it and look at it, like I said in chapter 4, but we're not going to worry about that for right now. Right now, we want to get really good at applying our quotient rule just in general. So that's the sort of process of breaking things down. I'm going to have you try one. So you can keep the formula. No, I'll rewrite the formula for you guys. So the quotient rule that you're going to try, we have sine x over ln x. I'll write that a little bit bigger. Sine x over ln x is the function that we're going to try. I'm going to rewrite the quotient rule up here. So f prime of x times g of x minus g prime of x times f of x, all divided by g of x squared. Okay, so I want you to try this one out. Sine x over ln x. See if you can figure out the structure. What is your f? What is your g? Find their respective derivatives. Carefully plug back in. I'll give you about 2.5 minutes to try it out, and then we will go through it together. Okay, take about a second. All right. So again, the order is incredibly important here. So we don't have a choice in what is our f and what is our g. Our top function is always our f function, and our g function is always the bottom function. So here, my top function is sine x. My bottom function is ln x. So I set up my f and my g accordingly. Now I want to find each of these functions' respective derivatives. The derivative of sine is cosine. The derivative of ln x is 1 over x. Okay, so this is sort of the first big part, is just finding each of their respective derivatives. And then the second part is just plugging in everything correctly and carefully. So here we're going to do f prime times g. So we have cosine x times ln x. Okay, that's the first part. That's my f prime times g. Minus g prime times f. So g prime times f, we have 1 over x times sine x. That's the numerator, divided by g of x squared. So my g of x is ln x. So I have ln x squared. So that's what my quotient rule is going to look like when I apply all the pieces. Okay, so again, we don't do a whole lot of simplification. I don't see anything here that I would simplify. I do want to point out that the 1 over x, you cannot bring that inside the sine of x. They are two different functions. So the solution would look just like this. Okay, so now that we've done a couple of those, you may have guessed we are going to do the equation of a tangent line problem here. So the function, I'll write it a little bit bigger. is ln x plus 2 over x cubed. So you can see that the function is a quotient here, okay? And we want to know what's happening at x equals 1. So again, think about our process for finding the equation of the tangent line. Again, what's different here is that we have a quotient in for our function, so we have to be a little bit careful about how we handle that. But we need a point, we need a slope, and then we can put it all together to get the equation of a line. Okay, so take 3 minutes. Okay, see if you can work this out. Again, following the same process and applying now what we know about derivatives, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we need a point and a slope. So we're going to start by finding the point by taking our x equals 1 and plugging it into the original function. So if we plug in a 1, we get the natural log of 1 plus 2 divided by 1 cubed. The natural log of 1 is 0. 0 plus 2 is 2. 2 divided by 1 is 2. So when x equals 1, y equals 2. So our point is 1, 2. Okay. So now we also need the derivative here. And so in order to do the derivative, we're going to have to do a quotient rule, right? So we pick our top function to be our f. So we'll do this sort of over here. So our f of x is the natural log of x plus 2. And our g of x is x cubed. Okay, now we want to find each of their respective derivatives. The derivative of the natural log of x is 1 over x, and the derivative of 2 is 0 because 2 is a constant. And then over here, the derivative of x cubed is going to be 3x squared. Okay, so now we have all our pieces. So we want to go ahead and plug this into the quotient rule formula. So we're going to do f prime times g. So we have 1 over x times x cubed minus g prime times f. So we have a 3x squared. Now my f has 2 terms in it, so I'm going to use parentheses. Natural log of x plus 2 divided by g squared. So x cubed squared. So I found the general derivative first. This is my f prime of x. But in order to find the equation of the tangent line, I need to figure out the value at 1, because that's going to help me find the slope. So I need to plug in a 1 into all these places. Let's see what happens. So we have 1 over 1 times 1 cubed minus 3 times 1 squared times the natural log of 1 plus 2, all divided by 1 cubed squared. So let's see what that is. So 1 over 1 is 1 times 1 is 1. So this first term gives me 1. Now I have minus, now I have 3 times 1 squared. So 1 squared is 1. So I have 3 times 1. And then over here, I have 0 plus 2, which is 2. So 3 times 1 times 2. So 3 times 1 times 2 is 6 divided by, and then 1 to anything is 1. So this is all 1. So I have 1 minus 6 divided by 1. So that gives me a slope of negative 5. Okay, so now I have a point. I have a slope, right? I gotta be really careful with the algebra here. But now I can put that all together to get the equation of the line. So let's go ahead and we'll just do it here. So y equals mx plus b. So y equals negative 5x plus b. So the negative 5 is from the slope. Now I'm going to plug in my point. When x equals 1, y equals 2. So I have 2 equals negative 5 times 1 plus b. So I'm going to add the 5 over to the other side. And that's going to give me b equals 7. So now I have the final equation of my line, which will be y equals negative 5x plus 7. Okay, so I do want to point out that there is quite a bit of algebra happening in the background of this problem. So yes, we are taking derivatives, but we're also plugging values in, being really careful with our subtraction and division. So if you are getting tripped up by the algebra, then I recommend that you try to practice that quite a bit to get comfortable with it, because you don't want the algebra to get in the way of the calculus. Okay, so this is the example of the equation of the tangent line. What I want to do next is I want to do a harder example of the quotient rule and then a harder example of the product rule. So the ones that we've looked at so far are the pretty standard examples that when we separate things with f and g, we get basic functions that we can just take the derivative. That is not always the case. Sometimes the functions we are working with are complicated functions within a complicated function. And so things like order become important, things like that. So we're going to jump down to example 5. If you have the notes and are following along, we're going to jump down and do example 5 here, because example 5 is a quotient rule that involves chain rules. Okay, so that obviously is going to make it more complicated. So this is definitely going to be a hard one. We have to be really careful with our algebra as we go along. I'm going to rewrite it just a little bit bigger. So we have sine of x cubed plus 2x minus 1 over e to the 5x cubed. Okay, so we're going to do a quotient rule here. Our top function is f and our bottom function is g. But when we take the derivatives of each of those things, we have to use a chain rule because the derivative of sine of something complicated or e to something complicated requires that we go back and use what we learned in the chain rule section to find the derivatives of those pieces. So that's what's going to make this complicated, but it's good practice to sort of interweave these things together. Okay, so I want you to try this out. Definitely feel free to refer back to your chain rule notes. I'm going to give you about 4 minutes just because there's a lot of algebra here. See how far you can get. It's okay if you don't finish the whole thing, but hopefully you can at least set up sort of the f and the g and the derivatives, and then try to carefully plug it back into the quotient rule. See how far you get. We'll go through it together, like I said, in about 4 minutes. Okay, take about 30 more seconds. Okay. So again, this one's more complicated because within the quotient rule, we are going to have chain rules. Okay. So we have to be really careful when we're finding these individual derivatives because they're not basic, right? We have to think about what the rules are, how we use them, and how we apply them here. So as we talked about sort of before spring break, there's different ways to approach them. Some are longer with z substitutions, and some are more sort of shortcuts, if you will. The shortcuts are helpful here just for time and space, but if you did a z substitution, that's fine. You should get the same thing. So for the sine function, we know that the derivative of sine is cosine. So when we do the outside part of the derivative, we get cosine of x cubed plus 2x plus 1. So when we change the sine to cosine, the inside stays the same, but then we multiply this by the derivative of the inside. So the derivative of x cubed is 3x squared. The derivative of 2x is 2. So my full derivative has two terms and it ends up looking like this. Similarly, when we do the derivative here with e functions, we get the same thing back. So e to the 5x cubed, but then we have to multiply this function by the derivative of the power. So we take this 5x cubed and we take the derivative of that. So that's going to give me 15x squared. I like to write that term in front. It doesn't matter if you write it in front of the e term or after, because it's multiplication, it means the same thing. But for me, the matter of preference, I just like to write that term in front. Okay, so now we have all the pieces. So now we have to carefully arrange these and plug them into this formula. So this is obviously going to take a whole lot of space here. So I'm going to try to get it all fit across one piece of paper. We'll see if we can do it. So we're going to do f prime times g. So f prime is this cosine function. So we're going to have cosine x cubed plus 2x plus 1 times 3x squared plus 2. That's my f prime. Times g. So my g here is e to the 5x cubed. Okay, so that's the first part. This was, like I said, this is my f prime times g minus, now I'm going to do g prime times f. So I have 15x squared e to the 5x cubed. That's my g prime times my f term, which is sine of x cubed plus 2x plus 1. Somehow managed to get that all across. Divided by g squared. So I go to my g term. Again, I'm going to put in parentheses e to the 5x cubed squared. So this one is not trivial, right? This one is not easy. There's a lot of pieces of things happening here. And so we have to be really, really careful and deliberate with every step we take, right? With every calculation we do, with every derivative we're looking at, we need to make sure that we're being really careful because there's so many places where we can go wrong, okay? So this is an example, like I said, of one of the harder types of quotient rules that may come up. I want to do something similar. And since we have a little bit of time, go back and do one of the harder product rule problems, because again, these things are intertwined, this idea of chain rules within product rules, or you could even have a product rule within a chain rule. So these are sort of the harder things that come up. So I'm going to switch back and we're going to jump down to example 6 here. That's the quotient rule. So we're going to try to find the derivative of sine of x all cubed times the natural log of x squared minus x plus 1. So the first thing I want to point out here is just that this is a product rule because we can separate the two functions. But again, when we separate the two functions, it becomes clear that each of those functions requires a chain rule to find the derivative. So again, we've shifted back to product rule, so I'll write the product rule formula up here. But we're doing chain rules within the product rule. Okay, so when we do these, you just want to make sure that you're being careful about the quotient rule, about the chain rule. You can do z substitutions, but I do encourage you that if you're comfortable with the shortcuts to try those out. Okay, so for the product rule, you have f prime times g plus f times g prime. That's our product rule up here. Okay, so I'm going to give you, again, about 4 minutes. Try this out. This is good practice on the chain rule within this. You're going to pick the first one to be your f, the second one to be your g. You're going to find their derivatives using the chain rule, and then we'll put it back together to get a final solution within the product rule. Okay, so try that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So the first thing we have to recognize here is that sort of the outer part of this derivative is a product rule, that we have two things multiplied together that can be separated. So we start this off as a product rule. This is one of the more complicated things that's going to happen with these derivatives is getting comfortable understanding where to start, whether it's a product rule or a chain rule or a quotient rule, looking at them and sort of understanding how to start the process. So that's something we have to practice, and hopefully through homework and things like that, you'll get more comfortable figuring that out. So here we have a product rule because we have two things multiplied together. The first one we're going to call f, which is our sine of x all cubed. The second one is our g, which is the natural log of x squared minus x plus 1. So now we need to find each of their respective derivatives. So when we go to do that, what we see is that we do have to use a chain rule here to find each of their derivatives. For the f of x, we do have parentheses to a power. So we're going to use that chain rule here. So I'm going to deal with the outside power first. So I have 3, everything inside stays the same, and subtract 1 from the power. So I have 3 times sine x squared, but then I have to multiply that by the derivative of the inside. So the derivative of the inside is whatever's inside the parentheses, which was the sine of x. The derivative of sine of x is cosine of x. And then over here, we have to do a natural log chain rule. So the shortcut on the natural log is that whatever's in the argument goes in the denominator. So that's the x squared minus x plus 1. And then the derivative of that goes in the numerator. So the derivative of x squared is 2x minus the derivative of x is 1, and the derivative of 1 is 0. So now I have all my pieces. So I'm going to put them together with the product rule. So I'm going to do f prime times g. So here again, this is going to be a little bit long. So I have 3 sine x squared times cosine x. That's my f prime times g. So ln of x squared minus x plus 1 plus the second part, I'm going to have f times g prime. So I'm going to do that in another color just to sort of show you what's going on here. So my f is sine of x cubed times g prime, which is 2x minus 1 over x squared minus x plus 1. So my final derivative looks like this. It's very long within the product rule here. And so the more complicated the derivative is, the less simplifying that we do overall. The only thing that might get simplified is this last term. And I'll show you exactly what that might look like. So when we have something that is a quotient and we are multiplying by a single term, you can multiply that term into the numerator. So this could be written as sine x cubed times 2x minus 1 over x squared minus x plus 1. So you can bring that term into the numerator. If we do that, we need to put parentheses around what's in the numerator so we know that the sine x cubed multiplies both terms. So this term can be simplified into this, but otherwise there's not really any other simplification we would do here. Okay, so again, when you're doing these, try to be really careful as you lay everything out. You know, they get more complicated when you add in things like chain rules, but otherwise the process is always to identify the f and the g, separate them out, find their derivatives, put them back together with the formula. Okay, so we're going to stop here for today. There is a review on all the different derivative techniques tonight from 5 to 6. So if you think that'll be helpful in preparing for Monday's Chapter 3 quiz, please stop by. The link is on Zoom and emailed to you. Otherwise, have a great weekend, and I will see you guys all on Tuesday.